Okay, so I guess it's just about time to start again. And the next speaker is Bryce Clarke, talking about a diagrammatic approach to symmetric lenses. So go ahead, Bryce.
Okay, thanks Martha, and thanks to the organisers for this conference. It's a real privilege to be able to speak here. And so today I want to talk about a diagrammatic approach to symmetric lenses. And to just give a quick overview of the talk, basically every box in this picture that you see is going to be some kind of category or bicategory that will be discussed. And the idea of this talk is to somehow develop a diagrammatic framework for lenses of two main kinds, so asymmetric lenses and symmetric lenses. And so by diagrammatic framework, what I really mean here is that everything that we do with lenses can be built up from simple building blocks, namely the three classes of functors I have at the top of the picture here: discrete operations, bijective and objects functors, and fully faithful functors. And we can construct commuting diagrams in CAT, and everything that we want to understand about lenses can be done in this framework. And I guess the second goal of this talk is to use this framework to, I guess, more deeply understand the relationship between symmetric lenses and spans of asymmetric lenses. Okay. And so any talk about lenses should really start with what kind of lens are we talking about? And so the lenses I want to talk about today, the idea of them is to provide some kind of structure that maintains consistency between the states of a system. And here we'd like to think of a system as some kind of category whose objects are the states of the system and whose morphisms are the updates or transitions between the states of this system. And so a lens is some morphism between systems, which keeps these states consistent. And so, as I mentioned, there's two kinds of lenses I want to talk about. The first one is probably the most familiar, at least to this audience, known as asymmetric lenses. And so, and specifically today I'll be talking about asymmetric delta lenses, which are a generalization of the concept of a very well-behaved lens, and we'll discuss this a bit later. But an asymmetric lens consists of a get and a put. And the get, what it really does is it says, well, for any morphism or for any change in our system A, we can produce a morphism or an update in our second system B. But the put is a slightly different operation. The put says, well, if we have a state in our category A and we produce a state in our category B, now if B has to change state to something via an update U to a state B, we want to be able to return consistency from this new state B to our system A. And so this put operation produces this new update, phi, which is dependent on our state A and our update U. And the put get law says that well, indeed, these two systems are now consistent because A dash goes via this get functor to B, and phi goes via this get functor to U. And so this is what an asymmetric lens is, but we can see why it's asymmetric because the get functor and the put functor treat these morphisms and how they propagate them between systems very differently. A symmetric lens is a generalization of an asymmetric lens, which sort of puts both of these forwards and backwards or left to right operations here on the same level. So if we think of an asymmetric lens as some kind of function-like morphism, then a symmetric lens is some span-like or some relation-like morphism between these systems. And so we start with a set of states for a symmetric lens and some span between the object sets or between the states of these systems. And these x's, this set X witnesses the consistency between states of these systems. And so if we change something in system A, we can use the propagation operation of a symmetric lens to produce a corresponding morphism in V, and vice versa. Now, this is all very good, but some of the disadvantages of this sort of operational or algebraic approach is that it becomes very difficult to prove things because the notation's quite heavy. It becomes very difficult to construct examples and prove that these examples all satisfy axioms, which I haven't stated here, such as preservation of identities and composition. And we sort of need to carry all of this around when we're working. So what we'd really like is to understand lenses as something we already understand and a bit simpler, which are just diagrams in CAT. And so how I would like to do that is to really introduce just 3 simple classes of functors with certain properties and build up everything we sort of currently understand about lenses using these functors. And so the first class are discrete op vibrations. And so a discrete op vibration is just a functor which says that for every state A, little a, and every update or morphism in f of A to B, we can find a unique morphism W, which lies above U. And so we sometimes call W the lift of U. And so here we can see a very simple example of what a discrete op vibration would look like. And I should explain the use of color here. So in this red object here has a fiber which is given by the set here of red objects. And likewise for the blue is this set of blue objects. And the discrete op vibration says that if we have a morphism between the red and the blue objects here, we get a function between these sets of fibers. And so next we have bijection objects functors, and these are very easy to understand. It's just a functor whose object assignment is a bijection. And so again, we can see this is some kind of lifting property, which says that for every state B in our system or our category, there exists a unique state A which lies above, lies in the fiber of B. And so again, here we have a very simple example where I've explicitly labeled our states so we can easily see the bijection between these objects. And lastly, we want to see fully faithful functors. And again, fully faithful functors have a kind of lifting property. It says that for every pair of states, A and A dash, in a morphism from FA to FA dash U, we can find there exists a unique W from A to A dash, which lies above U. And so when a fully faithful functor is injective on objects, we usually call this a full subcategory. And here we can see a very simple example of a fully faithful functor as well. And so this would be a full subcategory up to equivalence. And so using these 3 classes of functors, we want to somehow build up our understanding piecewise. So next we come to the definition of a cofunctor. And so normally we talk about functors between categories. And we know that lenses aren't exactly just functors between categories, but functors with some extra structure. And so the category of cofunctors, small categories and cofunctors, are a different kind of morphism between categories. And so what a cofunctor is it says, well, give me a state in A, produce a state in B, and now if we change B somewhat, we want to choose some kind of morphism, some kind of lift or update in A, such that the domain and codomain of these updates correspond. So A dash is consistent with B here under this object assignment. And notice that the direction of a cofunctor goes in the direction of the lifting of morphisms. And so we think of a cofunctor as, again, by this, for each update of this form, we have a chosen lift in our other system. And this lifting respects identities and composition. So that should tell you that somehow it should be built up of something which behaves like a functor. And so to understand this, recall first that, say, for small categories and functors, we can see every functor is broken up into smaller parts. A functor can factorize as an orthogonal factorization system of a functor into a bijective on objects functor, followed by a fully faithful functor. And it turns out we can do a very similar thing with cofunctors. The category of small categories and cofunctors also has an orthogonal factorization system, where now every cofunctor can be represented as a diagram in CAT, namely a span of functors whose left leg is a discrete op vibration and whose right leg is a bijective on objects functor. And so now we understand this sort of mysterious thing, which is this cofunctor, which, if you recall from a couple of slides ago, describes the put of a lens. And we've just now understood it as a diagram in CAT. Now, one might also ask the question, how can we understand functors and cofunctors on the same level? Is there a way of unifying both of them simultaneously? And that's where we get to the bicategory now of MEALY morphisms. And so again, this bicategory has objects are small categories which represent our systems, but now the morphisms may be represented again as spans. But here, it's a span of functors where only the left leg needs be a discrete op vibration and the right leg can be any functor we like. And we can see this as some kind of partial map between our categories, because if this discrete op vibration was the identity, we would just get functors back out again. But we can also see cofunctors as an example, because if this functor was bijective on objects, this would just be a cofunctor. And so again, this is some kind of representation of what a MEALY morphism does. There's a span which, and so the objects of X now are again witnesses to some consistency between this state in A and this state in B. And if we make some change to our system in A via W, we want a way to propagate this change to a change in our system B and also produce a new state X dash, which witnesses the consistency of A in this new state in B. And so why are these called MEALY morphisms? I took this name from a paper of Robert Perret. And the idea is that they generalize MEALY machines, which come up in computer science. And so recall that a MEALY machine is just a set X of states and sets A and B, which are our input in our output alphabet, together with this pair of functions, which for every state and for every word in our input alphabet produces a new word in our output alphabet, and also this transition, which produces the next state to read from. And so really, a MEALY machine can be seen as just a MEALY morphism between free monoids on the sets A and B. And again, this picture sort of explains a bit better what's going on. And so why do we care about MEALY morphisms? Well, MEALY morphisms are exactly the bicategory you get when we combine these three classes of functors that we considered earlier. So every MEALY morphism, here we see a MEALY morphism as factorized into a discrete op vibration going in the opposite direction together with a functor, but this functor could be further broken up into a bijective on objects followed by a fully faithful functor. And so really every MEALY morphism can be understood as built up of these three classes of easy to understand functors. Okay, so now we come to lenses, and MEALY morphisms aren't explicitly used here, but they'll be used a bit later in the talk. Asymmetric lenses, I guess another combination of these functors and these cofunctors, where now we see that the get of a lens, of an asymmetric lens, is given by a functor. The put of an asymmetric lens is given by the cofunctor. And we can represent this as, again, simply as a commuting diagram in CAT. And so here we have the functor from A to B, and also the cofunctor, which goes from B to A. And so I haven't really explained what this category lambda here represents for a cofunctor, but you should think of this as the category of chosen lifts of our cofunctor. So it contains all the morphisms which we choose via this lifting. And then this functor phi sort of faithfully includes them into A. And so there's heaps of examples of asymmetric lenses. Firstly, if A and B are codiscrete, then we get our very well behaved lenses back out again. And these satisfy the laws that you're probably very familiar with. We also get split off vibrations as examples of these asymmetric lenses. These are sort of least change asymmetric lenses in literature. And also if A and B are monoids, then we can see a section retraction pair as some kind of asymmetric lens. And so here I've also got a very simple running example for the rest of the talk of an asymmetric lens where here we've got this category, this pre-order with 5 objects and some arrows. This functor takes it to this co-span. And now this discrete op vibration, F bar, chooses some of the arrows, chooses some lifts above this morphism and this morphism. And then this category phi includes these chosen lifts into the domain of F. So really we can see how these functors, this discrete op vibration, this bijector and objects functor, together with this commuting diagram capture all the information of what is happening here with the states and the updates. Now, I'm shortly running out of time, but let's see if we can get through the rest of this. We can construct this bicategory of spans of asymmetric lenses. And so asymmetric lenses sort of sits inside this bicategory of spans of asymmetric lenses. Now, the interesting thing about this bicategory is that the 2 cells are not what you would first expect. The 2 cells are just given by these red arrows here, which make everything in this diagram commute. Whereas normally you would expect a 2 cell to be some kind of lens from X to X dash. And so the paper goes into more detail about how we actually construct this kind of interesting bicategory. And so for our running example, here we just had on the right hand side, we had the lens that we considered before, but here we have another lens which has a common domain. And here the codomain of this lens is just a span. And so we have some chosen lifts given by G bar, this discrete op vibration, and gamma now includes those into this common category. And so we see this system as sort of some system that maintains consistency between these 2 smaller systems. Now, symmetric lenses, again, can be seen as certain diagrams in CAT. And now we can see these as suitable pairs of MEALY morphisms. So what do I mean by suitable? Well, first we can see that there's a MEALY morphism in this diagram from A via X plus to B. And secondly, we can see there's a MEALY morphism via F bar to X minus and then to G to A. And by suitable, we mean that X plus and X minus have the same objects. And G bar have the same object assignment, and likewise for F and F bar. And there's a way of seeing every span of asymmetric lenses as a symmetric lens just by composing these functors in the diagram. And so this is the running example that we get from just composing the functors in our previous diagram. And so really all the symmetric lens cares about is how we can move and propagate updates from one side to the other. It doesn't care about how we do that via some intermediate system. Now, without this intermediate system here, you may ask yourself, well, given that every span of lenses is a symmetric lens, can we also see symmetric lenses as spans of asymmetric lenses? And it turns out that we can do that. Now, because the main theorem of this paper, which
Right,
contains all the details.
Your question time.
Yep, I'll wrap up now. Thank you. And so the main theorem is really just this adjoint triple, so we can produce this left adjoint and this right adjoint, and the details of how you construct that are really interesting. And so really just to summarize, we had two goals, which was to develop a diagrammatic framework for lenses, and here we can see how we've done that. And our second goal was to understand the relationship between these symmetric and asymmetric lenses. And here we see this explicit adjoint triple between the HOMs of these bicategories. And so symmetric lenses are fully faithfully embedded in two different ways into spans of asymmetric lenses. Thank you.
Thank you very much. Thank the speaker. Do we have any questions for Bryce? Okay, so I have a very kind of basic question. I don't know a huge amount about lenses. Can you say a little bit more about the sorts of places that these would be, that lenses are applied? So I think, is it database theory, is that right? And also then what your work kind of contributes to those applications?
Sure. I guess we saw in the previous talks how lenses are really used in programming. And these kinds of lenses that I'm talking about are used more prominently in databases, and these original definitions of asymmetric and symmetric lenses were proposed in computer science by Diskin and his colleagues. And that was in model-driven engineering. And so I guess really what I hope that this contribution makes is that instead of working, I guess, explicitly with elements and we can work more implicitly with just doing all our calculations in a very familiar category, which is CAT, and we can do pullbacks with these diagrams, and we can sort of just use the properties of these functors rather than having to explicitly compute details, which can get quite messy and so on.
Sure, thank you. That's a nice explanation. Any more questions for Bryce at the moment?
I have a very basic question.
Go ahead.
On the in the very beginning slides, were those technically, you wrote functor and cofunctor on the very first slide or so? Was that technically a functor and a cofunctor? And if so, what were the, yeah, I think it was there.
For an asymmetric lens?
Right there on the left. Yeah. What are these categories and functors and cofunctors being written there? For some reason, I thought A and B were sets in this example, but maybe I...
Right, so A and B, all the systems that we consider are categories.
Are categories, okay.
Yeah.
And so would these be like the category that's like the contractible groupoid on a set A or something?
Right, exactly. So when we want to get our familiar example of very well behaved lenses, we just use the co-discrete categories. So yeah, the contractible groupoid on
I see. Okay.
Constructed from this set. And so there we don't really care about how we get from one state to the other. We just care about the start and end points. Whereas here we care about, well, by which method do we change states?
I see. So a functor there is completely determined by what it does on objects, and a cofunctor is this thing you wrote there between two contractible groupoids. Okay, cool. I didn't. No, wait, a cofunctor between contractible groupoids is both of these data, right? Not just the second.
Here, so this example here is what we're talking about. And so this function between the sets completely determines the functor, the get functor. And this function here, satisfying these three laws, completely determines the cofunctor.
Okay, thanks.
Yeah.
Okay, if there's any more questions, you have to get in quick. Okay, so let's thank Bryce again, and then we'll move to Michael Johnson's talk.